Massive MIMO and beamforming are already impressive, but here's the real surprise. In 5G, a single base station can talk to dozens of users at the same time, on the same frequency, without chaos. How is that even possible? Let's break it down. In this video, we're going deeper into advanced massive MIMO and beamforming, the technologies that make 5G fast, reliable, and scalable. We'll see how 5G serves many users simultaneously, how beams are intelligently shaped, and why these ideas are also the foundation of 6G networks. Traditional cellular systems used just a few antennas at the base station, but massive MIMO changes the game by using tens or even hundreds of antennas. Instead of broadcasting signals everywhere, the base station becomes smart. It can focus energy, separate users in space, and reuse the same spectrum again and again. Think of it like upgrading from a flashlight to a controllable laser system, except we can create many lasers at once. Beamforming is the secret sauce. Rather than sending signals in all directions, the base station shapes the wave so that it constructively adds up at the user's location and cancels out elsewhere. There are different types: analog beamforming, simple but limited; digital beamforming, powerful and flexible; hybrid beamforming, the sweet spot for 5G, especially at wave. The result? Higher signal strength, less interference, and better energy efficiency. Here's where things get really exciting. With multi-user MIMO, the base station serves many users simultaneously on the same time and frequency resources, but with different beams. Each user gets their own spatial channel. Pushpin analogy time. Imagine a teacher in a classroom, but instead of speaking loudly to everyone, the teacher whispers different messages directly to each student at the same time, without anyone else hearing it. That's multi-user massive MIMO. But how does the base station know how to shape these beams? That's where precoding comes in. Precoding mathematically adjusts the transmitted signals so that desired signals add up at the intended user. Interference is minimized for other users. Popular precoding techniques include zero forcing, MMSE precoding. These algorithms turn complex wireless channels into clean, parallel data streams. Of course, all of this depends on one critical thing: accurate channel estimation. The base station constantly learns the wireless environment using uplink pilots, channel reciprocity in TDD systems. This allows beams to be updated in real time, even when users are moving. In 5G, this process happens milliseconds at a time, fast enough to track smartphones, cars, and even drones. Now let's visualize it. Picture a dense city, dozens of users, high-rise buildings, constant movement. You see multiple beams shooting out from a base station, each beam locked onto a different user. As people move, the beams smoothly track them, reshaping instantly. This is what enables high-capacity stadiums, crowded shopping malls, ultra-reliable industrial networks. In 6G, these ideas go even further. We're talking about cell-free massive MIMO, AI-driven beamforming, terahertz communications, beams that adapt not just to users, but to the environment itself. Massive MIMO won't just support devices, it will support entire intelligent systems. So here's the big picture: massive MIMO and beamforming, multiply network capacity, reduce interference, improve energy efficiency, make dense 5G and future 6G networks possible. This is spatial signal processing at its finest.